Hi, my name is Chima and welcome to Lab 2 Motion of a Falling Object. In this lab, we will observe the falling object with two forces acting on an object, the weight force and the drag force. And the equation for each forces are given here. The weight force is mass times gravity times j hat, and drag force is b, the coefficient of drag force, times the magnitude of velocity squared times j hat. And the j hat is the direction of an object, which in this case is y. And notice that the weight force is negative because the object is moving downward to the negative y direction, and the drag force is positive. And the drag force or the air resistance always have the direction opposite from the motion of an object, which the motion of an object is going down or the direction will be negative. So in this case, the drag force will be positive. So in Tracker, I've set the coordinates such that the right side be positive x direction and up is positive y direction. And the camera was slightly tilted, so I turned my coordinates slightly to the right, following the pig, which is our object's motion. So it's like that. We can see that the pig falls down to the negative y direction. And to avoid the acceleration that may be caused by my hand, human right here, I started collecting data a few milliseconds after the drop. So I'll start right there. And in Python, I started a program with plugging in what I know, which is the pig's mass and the initial position and velocity of the pig. And to find the initial velocity of the pig, we use the equation that we learned from lab 1 and plug in right here. And notice that the delta t is significantly smaller than that of the observation because we want the most accurate result we can get. Smaller delta t, the more accurate result we can get. G is gravity 9.8. J hat is the direction of an object, which is y, what I said earlier. And B is the coefficient of the drag force. And we can find this number by picking random numbers until our results gets closer to that from the observation. And in while loop, I inserted the two equations mentioned earlier, which are the weight and the drag force. And the net force would just be the sum of the two forces. The arrows will be used to represent the forces, and in order to do that, we have to make sure the units of the both sides of the equation are the same. So we want meters, and weight force is Newton, so the arrow scale will be helping this equation converting the units to be the same. So the arrow scale is newtons per meter. That will make the unit the same. And I make the arrow scale 10 so that it will fit the screen better. And if you run this program, we can see that the drag force and the weight force are moving in opposite directions. The arrow representing the drag force is pointing toward the positive y direction, which is this blue arrow, and the weight force is pointing downward, the yellow arrow, to the negative y direction. So now we're ready to make another program with no drag force. In order to do that, we need to make B, the coefficient of the drag force, equals 0, and the net force be the weight force, which is the only force we're dealing with right now. Then we can compile the program, save, and we can see that the only force acting on the object right here is the weight force, which is an arrow pointing down. Now we can compare all the results by keying in all the data we've collected from Python and Tracker and then graph all of them together. And we can see that the observation and the force, the position of the force without drag, is more closely to each other, concluding that there was drag force involved in the falling object experiment. And without the drag force, the predicted position would be different from that of the observed position. Now, to answer the first question, the terminal velocity is when the velocity is constant, making the acceleration zero, so the net force is zero, or the drag force equal to weight force. The terminal velocity can only be predicted by the model with drag force, because without drag force, there's no other force to cancel out the weight force that's going down, which creates acceleration, and we don't want that. Next question, the terminal velocity would eventually be the same because the system would approach the state of equilibrium. I created two new programs with everything being the same except the velocity. I make one of the programs velocity equals -10 and the other one will be 0. And the time on both, the final time will be 5 seconds, giving the object more time to reach equilibrium state. And if we run the two programs, we will get the same velocity, which is what we want. Right here, same velocity.